Okay, this is breakpoint 5. We are going over unit 9, which is galvanic voltaic cells and spontaneous redox reactions. Let's get started.
Professor Lane will take you to school. AP Chem is chemical.
Okay, so spontaneous redox reaction would be something like this. So we have zinc and copper reacting to form some zinc ions and copper, not in its ion form. So we can see that in its natural state, this has a oxidation number of 0. Copper would have an oxidation number of +2 here because of the charge on the ion right here. And then here we transition to zinc having the charge of +2, meaning that 2 electrons were removed, and copper would have a charge of 0. So zinc loses electrons because it goes from 0 to +2, so that's oxidized. And then copper gets reduced because it gains electrons and goes from positive to neutral. So we can see this copper ion gaining these 2 electrons from this zinc right here. And so this ionizes the zinc and makes the, reduces the copper. So, yep, again, we just have this copper getting reduced, just like I said, and the zinc is coming off. The zinc ion is coming off. So, these are called galvanic cells, also called voltaic cells. That's what allows these kind of spontaneous redox reactions to happen. Essentially a battery. So, the lithium batteries that you use for your phones or any other device are a type of redox reaction. So, that's a device that transfers electrons from one reactant to another through a pathway. And these are always spontaneous, which means in AP chemistry terms, they're thermodynamically favorable, which we will look at later in another unit. But that means they have a negative delta G, which means they proceed without any help. Essentially, you don't have to put any energy into the system. They will just proceed automatically. And then chemical energy is converted into electrical energy that moves electrons. Remember, electricity is just the flow of electrons. So here we have a drawing of the galvanic cell, and I tried to highlight the best I could. So we have the oxidation half reaction at the anode. That's what this little guy is called, the anode. And remember that with this abbreviation anox. Oops. So oxidation happens at the anode. That's a loss of electrons. Then reduction happens at the cathode, which is what this guy is called. So this copper cathode. And so that's red cat. And that's a gain of electrons. And so if we're losing electrons in the anode and we're gaining electrons in the cathode, that means that electrons always flow from the anode to the cathode. So that the electron flow is going to be this way, as the diagram illustrates. And so essentially that's all that's happening. It doesn't have to be always the anode to the left and the cathode to the right, but that's just how this one is drawn. And the only other thing of note here is this salt bridge, because we need to keep these solutions neutral. So these ions, these soluble ions that are usually our naps, sometimes something different, but in AP chemistry we usually see our naps come back up because they're not going to get involved in the reaction. They're just there to keep the solution neutral. So the positive ions are going to flow to the cathode because it's really negative over here because there's a lot of reduction happening. And then the positive anode, we're going to have a lot of negative ions, like the sulfate we're going to have come over here to facilitate and balance that chamber and keep it positive, or keep it neutral. So yep, as we just saw, they flow from the anode to the cathode. So in the same example, the zinc, which is in its natural state, loses the 2 electrons and falls off the anode into the solution, and is positive, like we see here. It's essentially the same thing, just a molecular view. And the copper will go from an ion in solution to a solid copper atom that sticks to the cathode. And remember, they flow from the anode to the cathode, these electrons. So yeah, all this salt bridge is just soluble ions in this like tube kind of thing. You can make it with even some just regular like chem paper. Usually you can make it with a salt bridge, just as long as it's able to flow through water and they do not react with ions in the solution to form precipitate, so we need to make sure they're soluble always. And if the solutions do not remain neutral, the reaction will stop, so that's why we need a salt bridge. And if there is no salt bridge, no reaction, and the voltage is equal to 0. So yeah, this is just greater showing a molecular view of the salt bridge. So you can see the sulfate leaving the negative reduction where this is getting more negative. You can see it leaving to the anode because it's attracted to the positive side, and then same thing with the sodium. So yeah, cations flow to cathode, anions flow to the anode. For a salt bridge, the positive goes to balance out the negative, and the negative goes to balance out the positive. Yeah, so the potential energy for electrons is higher at the anode than the cathode, and so all things naturally move to achieve a state of lower potential energy, and then a rock will naturally fall under the influence of gravity to obtain a lower gravitational potential energy. Yeah, the universe favors the lowest energy possible. Again, that's going into some thermodynamics that we'll cover later, but all you need to know is that they want to be at the lowest state possible because the universe favors the lowest potential energy that it can get. So let's look at some standard conditions for the cells. This is called the E0 cell is what we refer to this as. Like this little circle that you see above the E just means standard condition. So that means there's 1 molar concentration for the reactants and products. Our pressure is 1 atmosphere and the temperature is 25 degrees Celsius. And you add 273 to that to get to Kelvin, so it's 298 Kelvin. Standard reduction potentials. This is where we actually start calculating our standard reduction potentials, and they only give these to you for reduction. They'll only give it to you for the reduction, and so we have to know how to convert that to the standard oxidation potential. So this is it's a voltage, it's a numeric voltage number, and so if we're looking at this reduction potential, because it's gaining 2 electrons, let's say that the standard reduction potential was equal to 0.3 or something like that volts. It would be 0.3 volts. And then, so that would be the same because we're getting reduced. But if copper was getting oxidized, we would have to flip the sign and say this is a negative 0.3 because we're essentially flipping the whole reaction. And so it would be then copper gets oxidized to copper 2 positive plus 2 electrons. And so when you flip the reaction to become an oxidation reaction, then you also flip the sign on the E cell, like we see for, well, let's just say this was like the zinc getting reduced, then it would be positive, but our zinc got oxidized in the previous example, so we're going to flip the sign, and it will be a negative 0.3. So this is the reduction values. They used to give us whole tables, but now they'll just give it to you if you need it. It's based on the ability to attract electrons. So all the way down is the most likely to get oxidized. So the most negative is most likely to get oxidized, and the most positive is the most likely to get reduced. Yeah, so the species with the most positive, least negative electrons, or E, our reduction potential will be reduced as it has the greatest ability to attract electrons. So that's kind of like our electron affinity or electronegativity that we talked about in Unit 1. And an electron can only decrease its potential energy by moving to a species with the most positive, least negative reduction value. So let's practice calculating. So this is how we calculate. So the E cell, which is our overall cell potential. So E cell is our overall potential of the cell. Both the anode and the cathode equals the reduction potential of the cathode minus the reduction potential of the anode. So always just remember as cathode minus anode, or you can say plus anode, but you just have to flip the sign, which I feel like is a little more work. So I just do E cell equals the cathode minus the anode. So it would be the reduction minus the oxidation, and you'd usually flip the sign, but if you're doing the minus, you don't have to flip the sign. So yeah, so this would be this will be the most positive, so this will be reduced. This copper half reaction will be reduced because it's the most positive, and this nickel is the most negative, so it's going to be oxidized because they're going to flow to the lowest potential energy state. So then how we would use this, we do the reduction at the cathode because it's the most positive, so we're going to substitute in that value, the 0.34 volts, and then we're going to subtract the negative 0.25 volts, and this will equal, it would be plus, so that would equal 0.59 volts for our overall standard potential of the cell. And if you'll notice, this is a positive value, and for our galvanic cells, we will always have a positive E cell, which means it's thermodynamically favorable. There's another type we will learn about that always has a negative E cell, which means that it's non-spontaneous and not thermodynamically favorable. So we'll just skip this example, and I think that's all we have. Yep, so let me know if you have any questions down below.